So first, a little bit about me and the company that I work for. I'm the Chief Performance Architect at Percona, and we do services and support and develop software for MySQL. I hope that doesn't bias you against me. I also know a lot about lots of different databases as well, and I've been speaking and attending at Postgres conferences for several years. We also run a series of conferences ourselves. Our next upcoming Percona Live conference is in London on October 24th and 25th, and after that we've got one in DC in January, and then we have a really big one coming up in Santa Clara, California in April. And we continue to bring these conferences around the US and around the world. I think we'll probably be in South America after that. So enough about me and my company. Let's take a look at what we're going to talk about a little bit today. So the first thing that actually, there's a bullet point that should be on this slide, but there's a lot of bullet points on there already. So I'll just talk about it instead of writing about it. I'm going to sort of motivate the discussion, as they say, quote unquote. And then I'm going to show you step by step how you can go through capturing the traffic that your servers are generating, and how you can visualize and understand and analyze that data in a variety of ways to detect all sorts of things and derive all sorts of metrics about the systems. And then I'll finish up by showing you what these techniques are actually useful for. There's going to be roughly two parts of the presentation today. One is visualizing the TCP traffic and understanding what the systems are doing that you might find hard to observe otherwise. And then the second part of the day, we're going to be talking about formal understanding of performance and scalability and when that's useful, how you can use it to actually forecast out how your systems will behave beyond what you're able to observe and measure. So, for example, capacity planning. So just a little bit about my background and why I bring this particular perspective to this sort of data. My job, and I'm a consultant, and what I do for people is I improve the performance and quality of their systems. And in many cases, this involves tracking down extremely obscure performance problems. In other cases, it involves helping people understand where there are opportunities to optimize systems that they think are running okay, but they're just not looking at it in a way that shows them the problems that some of their users may be experiencing. So I look at systems, and I've learned over years how to measure them in great detail. You cannot optimize what you cannot measure. So the first thing that I've learned how to do, or the most important thing that I've learned how to do, and the thing that I do first in any consulting engagement, is measure in great detail and with as much precision as possible. So a few of the things that usually come out of this is improved quality of service, eliminating outliers. So for example, the people, there's a few different kinds of outliers. There might be a very popular portion of your site that doesn't perform as well, or if you have, say, a social media site like Twitter, it would be pretty bad if Justin Bieber's Twitter stream was slower than everyone else just because he's more popular than everyone else and he has more friends than everyone else, more followers than everyone else. So those are some of the kinds of outliers that you can discover when you stop looking at averages and aggregates and you start drilling down into the real details. When you find these things and you eliminate them, you can often reduce the load on the server, and you can improve performance and quality of service overall, because a server that's not as overloaded doesn't cause collateral damage to other things that are happening on the system. And of course, lowered latency, because the only thing that people really care about is response time. And you can look at that all the way from the user level, all the way down through the application and the database. Everywhere in the stack, what people really care about, or what they ought to be caring about, is response time. That's where money comes from. So my job is to observe performance problems, explain them, and then solve them. And normally, I will observe them first. So there are basically two kinds of things that happen. People call me in, they say, I don't know if anything is wrong, but can you find anything to optimize? So I do that by observing. Or they'll say, I have a problem, and I'll determine how I can repeatably observe the problem, because without good quality, tightly scoped measurements, you cannot, and repeatable conditions, you cannot solve a problem. Otherwise, it becomes trial and error. So then I explain what the problem is, and this is where things require knowledge of systems internals and so forth. And then the solution is usually obvious. So measurement is usually about 95% of the work in a careful, disciplined performance analysis and optimization approach. So this is all a little bit of preaching just to kind of set the stage for the way that I approach problems and why I'm going to be going into the particular things that I'll show you today. So the first question that I would have is, how closely are you measuring what your systems are doing? And this is not just monitoring. Monitoring is kind of a vague word, but if there were a long-running query on your system, would you know it? If the queries on your system ran or transactions completed in 80 milliseconds most of the time, and then suddenly some of them started to take 200 milliseconds randomly, or if you had spikes of transactions completing in longer than 5 seconds, but only 2 times a week at odd times of the day unpredictably, would you actually know that? Most people do not. In fact, it's usually very difficult to float these things to the surface and see where there are problems that need to be solved. But if 1 million users go through your checkout and purchase items from your website or whatever it is that they're doing, you know, stock trades or something like that, and every 10,000th user has a really bad experience, like an 8-second wait or something like that, or something that times out and completes on the back end but doesn't tell them on the front end that it completed or something, that's actually pretty bad. 1 in 10,000, 1 in 1,000, 1 in hundreds. That's really, really getting to be a bad experience for users. So it's very important to actually know whether things are going badly on your systems. And the other thing that I want to say here is don't take this to extremes, because something is always going badly. If you look closely enough, there's always variations in performance. I'll show you some of that later. So the big question is then, how do we discover these things, and how do we discover it easily and cheaply without getting into all sorts of years and years of effort, or purchasing expensive products that come with the magic button on them and promises from the salespeople that it'll just solve your problems. And I would submit to you that TCP traffic in systems that communicate over networks, which is almost all of what all of us are working with, is an incredibly useful way to find these performance problems cheaply and easily with the tools that are available to you now. You don't need to buy anything or learn anything from anybody other than basic system administration principles and a few little tools. TCP is great for performance analysis because it has call and response semantics. Most of the applications that communicate over TCP are going to send a request to something, and they're going to get a response back with the results of the request when it completes. There are a few types of applications that will fire and forget. MongoDB is perhaps famous for that. There are others. UDP is usually fire and forget, but TCP, most applications that communicate over TCP make a request, and then they block and wait for the response. So this is a very important thing. Postgres does this. Lots and lots of databases do this. Memcached, Redis, Oracle, SQL Server. You can apply the techniques that I'm going to talk about today to most databases, but it certainly is applicable to Postgres. And what that request and response means is that if you can measure when the request goes out and you can measure when the response comes back, that you have the two fundamental performance metrics. Those are the arrival time at the server and the completion time from the server of the request, whatever it is. I'll call it queries in most cases. In a lot of cases, you might want to understand transactions, but that's not exposed at the TCP level. That's something deeper in the database. But at the TCP level, we can see queries or requests, individual conversations back and forth with the server. So simply starting with the arrival time and the completion time, we can actually derive a lot more complicated information by aggregating and looking at these things over time and space. So we know the observation interval. That's when we start to measure and when we stop measuring. So if we measure for 10 seconds, then that's a 10-second observation interval. And queries per second is really easy. We just watch how many arrivals or completions there were. Take your pick. They're usually over a long enough period of time, they're going to be identical. And most of queuing theory and operations research is predicated on a long-term system where arrivals equal completions. You can find out the busy time, that is the portion of the observation interval during which some request was in execution, residence time on the server. And you can add up all of the execution times, and you can derive the total execution time. So none of this is complicated. This is all straightforward math. But it sort of like a fractal, it develops into something wonderful as you zoom out from it. So you can further derive using Little's law, one of the fundamental laws of operations research. From those metrics, you can gain throughput, concurrency, response time, and utilization. And I'll show you how those things are used on the systems later. I'm not going to go into all of them because I only have an hour, but I'll specifically show you throughput, concurrency, and response time. So down to the nuts and bolts. The first thing that you want to do is capture the TCP traffic. And this is a standard TCP dump. I'm running this on Linux, but it's going to look very similar on most other operating systems. And I'll just read off the command line from the left. TCP dump -S384. That means capture the first 384 bytes of each TCP packet. And I'm listening on any interface, so it's going to bind to all the interfaces on the server. And then there's a few options to format the output in ways that you'll see why it's useful. And then there's a long, complicated expression involving port 5432, which is the PostgreSQL port. And this expression actually comes from the TCP man page. You can find it there. And it essentially says, only capture packets that have a payload. Don't capture the TCP startup handshake where there's the SYN-ACK-SYN handshake sequence. Don't capture acknowledgments. Don't capture all of these other kinds of things. Only capture things that are at the application layer in the protocol, so to speak, so that you're getting the traffic as PostgreSQL would see it, for example. And then I'm just redirecting the output and storing it in this TCP file.txt file. I've got 3 lines here on the bottom of the page showing 3 samples of what comes out of this. Along the left, you can see that there's a timestamp with microsecond precision, and then IP, that's the protocol. Then there's an IP address, 10.220.146.79, and then the port number, the originating port number of this packet, 35805. There's a little angle bracket that shows the flow of traffic from one server to the others. That says that we just looked at the origin server, and then it's headed to the destination servers, 10.119.42.41, port 5432. So basically, this is a request coming into PostgreSQL. Somebody has sent a TCP packet to PostgreSQL. The last thing on the line is TCP 83, which means there were 83 bytes of payload in this packet, but we didn't actually capture that. We told TCP dump only to capture the IP headers and the TCP headers, which is the first 384 bytes. Okay? And then below that, we see PostgreSQL sending a packet back to the client they requested, and then we see another client sending a request to PostgreSQL. So this is the kind of thing that comes out of this, and this is something you can easily do on your production servers. TCP dump causes almost no perceptible load, even on extremely busy servers. The thing that happens, actually, if your servers are extremely heavily loaded, is TCP dump will start to drop packets. The kernel buffers will start dropping packets. And that's something interesting and important that you need to know. But basically, this should reassure you that TCP dump is not going to cause load on your servers. It may cause some I/O if you're putting this file in some place that's a disk that shouldn't be getting all of this I/O. You may even fill up your disk, so you have to have the normal precautions there. But otherwise, TCP dump is not an expensive thing to run. It's normally on servers that I run this on, I look at TCP dump. I stopped doing this a long time ago, but it was never above 1% CPU utilization from TCP dump. So it's really cheap and really easy, and you can just go do it now. TCP dump is usually installed by default, but if it's not, it's certainly in your package management. So then there's another tool that we can ingest the results here and consume that and output a massaged version of it that's very useful for further analysis. The response time, the arrival time and the completion time on the server here are shown on different lines. And lots of Unix tools like to process things a line at a time, so wouldn't it be helpful if we just took those first 2 lines and put them on one line together? And this is what this TCP model tool does. This is from Percona Toolkit, which is a very MySQL-centric set of tools that I've developed. But this one actually turns out This is a TCP-centric tool, so you can use this on any system. It has nothing MySQL specific about it. Percona Toolkit is available from percona.com/software, and I'll show you a URL to that later. So you just grab the file and put it into PT-TCP model, and you redirect the output, and what you end up with is a sample of something that looks like what's on the screen here. I've added column headers. That's just so that I can show you what the columns are. Those don't actually show up in the output. Along the left-hand side, there's a sequence number. That's the arrival order at the server. And then there's the start timestamp and end timestamp, and I've converted them into a numeric format rather than the date-time format so that you can do math on them easily. The elapsed time, that's the response time of these queries. And then the host and port that it originated from. I put that in there, but actually for all of our further analysis, we're just going to ignore the host and port. All we really need here is those fundamental metrics, the start time and the end time. And it's handy to just, while we're doing it, let's compute the latency of the requests as well. It makes it really easy to do a whole bunch of things with the data. But those are our, again, two fundamental performance metrics: start times, completion times. So what we can do with this, the first thing that I'm going to show you is just plot it as a time series. Plot the response times on the vertical axis against the time traveling from left to right during which I captured this sample. The sample that we're looking at here is about 30 seconds of traffic that I gathered. And I'll just give you a little bit of detail just for interest's sake about the server that I captured this off of. It was a MySQL server. It doesn't matter though. And it's running in the Amazon cloud. It's serving thousands and thousands of requests per second. Some number, I think it was about 8,000 or 10,000 requests per second overall while I was doing this. And it's not running very well. This server is heavily overloaded and is just about to be moved out of the cloud after this. They had pushed it as far as they could go in the Amazon cloud, and they were moving it to physical infrastructure for better performance. So this is on one of Amazon's largest instances with a whole bunch of EBS volumes under it. It's kind of as big as it could go. So that's just sort of for interest's sake of what we're looking at here, just for some context. Now, what we see on this image, again, each little point here represents one of the requests that went to the server. How high up it is represents how long that request lasted. And the vast majority of the requests are clustered around 200 microseconds or less. Okay? So pretty fast little requests, and they all turn into a little red blur along the bottom of the slide. However, there are some outliers, significant outliers, up to 0.3 of a second. For a database server that's running e-commerce queries, and most of them are under 200 microseconds, 0.3 of a second is kind of a long query. It's a very long query, in fact. And there's lots and lots of other ones, but there's something else interesting about this, and I want to see what you guys find interesting about this graph if you're willing to raise your hands and speak up. What do you see that's sort of noteworthy here? Yes, sir?
Spikes.
Spikes, exactly. There are spikes. What do you think the spikes mean? What's causing them?
My guess is if you reach a certain point where you've got, I mean, in Postgres lingo, I call it a checkpoint, something along those lines, where all of a sudden everything has to get flushed out, and now your query time is going to take a lot longer.
Okay, so one guess is checkpoints. Any other guesses? Locks. So who was here for Bruce's talk just before this? A bunch of people. Yeah, good talk. Lots of examples of how things wait on other things. One of the things that's maybe a little bit difficult to see about this that I would point out is that the spikes are angled a little bit. They're not completely vertical. So there's kind of a little bit of a diagonal line of long queries. It really is diagonal, and when you draw the line along it, it becomes more obvious. So it is locks, in fact. And what happens is, starting where that line is up at the top of the screen, there was a 0.3 of a second query, which was immediately followed by some queries that lasted for 0.2 of a second and then shorter and shorter and shorter and shorter. So they're kind of things piled up and then they trickled out. One of the things that I didn't tell you, which I probably should have told you ahead of time, was that I plotted these by completion time. So what we're seeing here is a query completion after 0.3 of a second, followed by a completion at 0.2 of a second, and so forth and so on. So what that means is that the 0.3 of a second query was holding some resource. And when it completed, the resource became free, and these other queries could go ahead and do their work. And I would guess that the actual service time of the second query was the difference between 0.3 and 0.2. That second query probably actually executed for 1/10 of a second once it acquired the lock that it was waiting for. So I don't know exactly what these queries are, and you can't tell from the data that I gathered because I didn't gather the actual query text, for example. I only gathered the TCP and IP headers. I don't have any information about the payload. But it's pretty clear that there is something that's holding resources, and when it releases it, other things trickle through and are able to complete. And this is one of the classic spike detection algorithms, is you look for completions, and when something completes and then other stuff completes after it, having waited for a while, you can sort of call them victims, and you can call the first guy the perpetrator, right? I happen to know that this is called by select for update. They basically had a queue in a database table. I'm sure that many of you have seen that kind of a pattern before, where you use a database queue as a database table as a queue, and you're doing something like select for update or something that's blocking, even if it doesn't have an explicit for update in it. And this actually turns out to be a problem in pretty much every database. I wish that nobody had ever invented select for update. It's a problem in Oracle. It's a problem in Postgres. There's a slightly different syntax in SQL Server, but it's a problem there too. There's almost always better ways to do this, but in this case, that's what was happening. It's select for update. And high-frequency polling would actually show you some of these things piling up in the transaction queue. So this is the first thing that kind of jumps out. When you just take this data, which again didn't require anything at the database level, you could have gathered this data from the application server. You didn't even have to be on the database server, and you could see this. So there is a problem on this server. From I don't know if there's a problem to 30 seconds later, I've plotted this and I see a problem. That was a pretty quick turnaround for, is there anything that we can optimize on the server? Now, I'm going to have to go and dig into the server before I figure it out that it's select for update queries. But at least I knew what to look for. Keeping with the same set of data. Yes, sir?
Just to hit on the select for update, do you have any comments, quick comments or thoughts on Kevin Grittner's SSI changes for Postgres and how they help?
No, I wasn't at that talk. I missed it, and I wish I had been in it. So the question was SSI, serializable. Right. And no, I wasn't at that talk. I'm sorry. I wish I had. Yeah. So I'll leave this for the people who read the slides later. So the next thing that I want to do is continue with this same set of data and see if we can dig in a little bit further and find more evidence of what might be going on based on the completions, because I plotted these by completion time. Maybe we can see something else in the completions. So I'll plot arrivals and I'll plot completions. And in this case, I'm actually going to bucket them into 5-millisecond intervals and count how many completions and arrivals were in each 5-millisecond interval. And then I'm just plotting them again. So on the vertical axis, we have the number of arrivals per 5 milliseconds, and on the horizontal axis, we have time passing. And when I look at this, I see a server that is receiving basically randomly distributed arrivals. If anybody would disagree, and if you can look at this and see sort of like the lady in the red dress in the Matrix, you're better at it than me, because I look at this and I see stochastic noise, essentially. And queuing theory assumes that there is a random, uncorrelated distribution of arrivals in any system that serves requests. It's called a Poisson distribution for the mathematically minded. And I think that's basically what's happening here. I don't see a clear pattern jumping out. And I would beware, I would caution you to beware of looking at things and finding patterns, because if you stare at things long enough, you'll find what looks at a pattern, and then if you drill into it, it'll disappear. So you want to look for things that are unmistakably a pattern. So that's arrivals per 5 millisecond. What about completions per 5 millisecond? The picture looks very different. And what's interesting is that we see a spike there along the left, maybe 1/5 of the way in from the left, but it is not where the spikes were before. I know you probably can't remember back to the earlier slide, so I will show you the slides together again in a little bit. But there's something going on there. And what I would like to do is know if there's a clearer way that we can pull out exactly. There might be some other spikes in here, or that might just be the varying nature of the users on the system or something like that. Maybe there's a clearer way to point out whether there is a problem with completions, a spike of completions that has been delayed for some time. So, maybe I'm graphing at too fine of granularity. Maybe I need to go finer. You can play around with those kinds of things, and oftentimes interesting properties will pop out at some particular point. I'll shortcut here in the interest of time, and go ahead and say that we should be looking at arrivals versus completions. So here's arrivals, drawn as a line instead of drawn as a scatter plot. And there's completions. And this is, it's not exactly easy to see whether there's anything really going on here. So I tried graphing a different way, and that spike, it went away. Whatever the anomaly was, I'm looking at it a different way now, and it doesn't seem to be there anymore. But it actually is there, because if we plot the difference of completions and arrivals, the spike jumps right out. So this is completions minus arrivals, which means that when the spike dips down, it means that the arrivals are continuing to come in, but the completions aren't happening. And then we see a spike up of completions. All of those completions are suddenly happening at once. And then as you look further to the right on the graph, you can see that indeed there are a few more. This sort of looks like an EKG. So there's a few more heartbeats on that graph where something else might be going on. It's not as severe as the one along the left, but it is happening. Something is happening there. So the difference there in the absolute number of completions versus arrivals is actually, it goes almost up to 30. So it's a pretty significant little spike of difference there. Now I'm plotting the first graph where we saw the spike of select for update versus this little stall of arrivals versus completions. And the other interesting thing that I would point out here is that there doesn't seem to be much of a correlation. Some of the spikes of select for update appear to have a little spike of completions versus arrivals around the same time, but there isn't a particularly big one there on the left of the graph where the huge heartbeat happens. Maybe that's an earthquake. But it looks like we're seeing different phenomena coming out. So there might be two different things happening in this system. Select for update might be causing one kind of a thing, and these arrivals versus completions might be causing something else. And indeed, if you look at that particular thing of the select for update that I was looking at before, if you count the number of queries that actually completed there, it was the 0.3 of a second. Below that, there's two that are around 0.2 of a second. So if you count down, there's what, maybe 8 or 10? It's not 30. This spike was around 30. So there really do seem to be different things happening on this server. And again, we don't know what they are yet. So this is my spike pileup detection algorithm, or one of the pileup detection algorithms, which is you start calculating this in smaller and smaller time windows. And when you get into a small enough time window where a spike, the stall of completions happens in one interval, and then the spike of completions happens a couple of intervals later, really, is you should seek for them to be separated by at least one observation aggregation interval. You can really see something start to jump out. Now, I'll tell you, if you make your aggregation interval small enough, you will see this. I guarantee it, on any system, no matter how well behaved. Because computer systems are networks of serving resources and queuing. Everything piles up in front of things in a queue. Your disk is a server in queuing theory terms, and there's a disk queue in front of it. Your CPU has a queue in front of it. Your network has a queue in front of it. All these kinds of things are queue and server systems. And these kinds of systems have queuing behavior. So if you make your observation interval small enough, you will see the queues. You will see pileups and clearing out. The big question is, at what point is that unacceptable? Is a 0.2 of a second pileup acceptable for you? Well, in a high-volume system such as this one, no, it's not. This was really causing bad performance on this system. Or this was the evidence of the bad performance on the system. So you want to look, but don't look too hard, because you will find the skeletons in the closet. There's another way that we can detect performance problems. We can do different things besides just counting the number of things that happen in every little interval of time. We can look at statistical metrics. Now, there's lots of different statistical metrics like averages or minimums and maximums and counts and all of those kinds of things. But most of them are relatively useless. For example, the average completely obscures the details about what happened inside of it. You just get a single number out and you don't know, for example, how variable the numbers that went in were. The variance to mean ratio, also called the index of dispersion, is a highly useful one because it shows you how variable the numbers that went into your aggregation were. It's normalized relative to the average response time or to the average magnitude of things that went into your bucket. So it actually lets you compare even very different things in comparable terms. Standard deviation is a related term. Standard deviation is the square root of the variance. What we're doing here is we're normalizing the variance itself. If you take the square root of the variance, you get something that has the same dimensions and units as the input data. So if we have the standard deviation of response times, they will look similar in magnitude to the response times, which means that standard deviation on a system that has 10-second queries versus one that has 10 microsecond queries are not going to be comparable. But if you normalize them relative to the input response times, you get something that you can actually compare meaningfully. So this is a very useful metric. So let's just go ahead and compute the index of dispersion over the same data set again. And we see 3 spikes. There is a spike on the very left-hand side, but that's just sort of because when we started the observation of the TCP traffic, we really kind of came into the middle of the stream. So that's just a startup artifact. There's really 3 big spikes here of index of dispersion. And you see most of the time it's kind of rock steady around 0. So there's very little variance in these 200 microsecond queries. The vast majority of them are piled up under 200 microseconds. Occasionally there's something much longer, or there's something much more variable, up to about 10. So this again shows us that something is different in those little time intervals, something interesting, something to look at. Why is a spike of highly variable performance interesting? It's because highly variable performance is bad. You want consistent performance on your servers. You want them to respond predictably. You do not want, as I mentioned earlier, checkpoints. That's MySQL suffers from checkpoint stalls. Postgres does too. Oracle does too. SQL Server does too. Most transactional systems have checkpoint stalls. And when there is a checkpoint stall, performance and quality of service just goes through the floor, right? So you really don't want that. But more importantly, highly variable performance is highly optimizable. Let's say we have an extremely simple workload on our server. All the queries are the same, but some of them don't run the same as others. What does that mean? It usually means that there is either a different execution path within the server, such as choosing a different index or not choosing any index at all, or reversing a join order in a query or something like that. Or it means that there's difference in data distribution, so that, for example, Justin Bieber has more followers than everyone else, right? So it usually means that there's something different about some of these queries that we might be able to optimize to make them run as quickly as the good ones. So digging into what's happening in these highly variable places is highly fruitful work. So here's all of the 3 things that I've shown you. The spikes of select for update, the spikes of we don't know what yet, and the spikes of we don't know what yet. So I basically, in a few minutes, I use GNU plot. You can use R. There's lots of other plotting packages. Don't use a spreadsheet, by the way. Misery, misery, misery. They will absolutely choke on large amounts of data. You want something like GNU plot or R to quickly, these are like one-liners, these little plots here. Take you a few seconds to create. Get familiar with them and get used to slicing and dicing your data in different ways, and you can very quickly tell whether there's something on the server that bears looking into further, without spending a lot of in my case, without spending a lot of my customers' money trying to do so. So that concludes part 1, figuring out whether there's a problem. In part 2, I want to take this and going back to those fundamental metrics that I mentioned in the beginning and all of the things that you can kind of compute from and then compute further from. I want to show you how you can get scalability and performance metrics out of your system and how you can actually forecast those into the future at loads that you can't measure because you're not currently experiencing, for example. And this is going to be a formal discussion of scalability and performance. I'm not going to use vague terms. But before I begin, I'd like to say, do you have, would anybody like to volunteer a definition of scalability? Because I have my own, but usually there's about, 40 people here, maybe 30 people? Yes?
If you throw more hardware, performance should go up, but some throughput should go up.
Okay, very good. That is excellent. Normally, when there's 40 people in a room, if you ask for scalability definition, you'll get 40 of them. Yours is very, very close to mine. So, and that's, Jignesh said, for the benefit of people who didn't hear him, if you add, essentially I'll paraphrase you, if you add more resources to a system, you should get a corresponding improvement in the system's capacity, throughput, performance. Various terms there. Okay? So scalability is actually a mathematical equation, and I'm not going to go terribly deep into the math, but I'll ask you to bear with me a little bit, because I love math, even if it's hard for me, which it is. And in this case, scalability can be considered along several different dimensions. In this case, I'm going to say if you throw more threads on a database server, if you throw more workers at a database server, you should get a corresponding increase in throughput. Okay, so that's how I'm going to define scalability for this right now. You can also define it as if you add more servers and you add the same amount of work to them, or if you add more CPU cores and you add the same corresponding amount of work, you should see a corresponding increase in throughput. So scalability is the favorite marketing buzzword of everybody who wants to sell you a database server, right? Linear scalability. Our system scales linearly. Scalability function looks like this. As I increase, in this case, concurrency along the x-axis, I should see throughput increase on the y-axis. And I'm putting a point of, doesn't matter what the units are, I'm putting a point on there, the little blue box, of 1. And if I double that, or whatever that is, it doesn't matter, it doesn't have to be doubled. If I increase along the x-axis, linear scalability is a straight line right through the origin, okay? This is most systems. This is not linear scalability. And it's cheating if you take those 2 points and you tilt the line down a little bit and you say, look, linear. You can draw a line through any 2 points, right? If it doesn't go through the origin, it's not linear scalability. And if we add, go out to an even higher concurrency, usually it drops off even further. So what causes this? Why do systems not scale linearly? By the way, as an aside, one of my favorite things to do is to go to trade shows and walk around to the various people who are selling servers, and they always have a little slideshow running, and they say linear scalability, and they usually have some benchmark numbers. And I like to just write down the numbers and just do a quick computation and figure out whether it's linear or not. They've usually got a line on the graph, and it's usually not linear. So it's a great drive-by exercise. See if you ever catch anybody with linear scalability. I have not yet. Linearly scalable systems are incredibly rare. And why are they rare? What causes nonlinearity? There are 2 things, as it turns out. One of the factors is that portions of the work have to be done in serial. Linearly scalable generally means that if you divide and conquer, you can get things done linearly faster, right? But if portions of the work have to be done serially and cannot be parallelized or divided and conquered, then no matter how many things you throw, how many workers you throw at the problem, there's only a certain amount that you can reduce the time to perform that task. If half of my task has to be done in serial, then no matter how many servers or CPUs or threads or nodes or whatever I throw at this thing, I'm never going to reduce the response time below 50%. So this is Amdahl's law, and this is one way of writing it. You've probably seen it expressed other ways, but this is a way that I'm going to be building on in the next slide. It says that the capacity, or in this case the throughput, of n threads is equal to the number of threads divided by 1 plus sigma times n minus 1. And sigma is this factor that varies from system to system. This is the portion of the workload that has to be serialized. So if sigma is 1/2, we would have 0.5 and n minus 1 in front of that equation. If we add on to the other factor, factor number 2 is coherency, also sometimes called contention. And this is the portion of the work that requires communication among different parts of the systems to complete. So lots of systems have locks, for example. The more transactions that we throw at something, the more they have to actually coordinate their work around locking, if they're using locks. The more CPUs that we throw on a system with a NUMA architecture, the more that they actually have to synchronize their cache lines. And as you increase those, the number of lines of communication between them increases as n times n minus 1, which is quadratic. And what that means is that as you add more to the system, instead of getting a continuing return on your investment, at some point that quadratic increasing cost of the coherency factor becomes more expensive than the linearly increasing resources that you're adding to the system, and therefore you actually reach a point where you get retrograde scalability. Your scalability levels off with Amdahl's law, and then it takes a dive with the coherency factor added in. So this is Neil Gunther. I didn't invent this. It's Dr. Neil Gunther's universal scalability law, which is probably going to be a classic of mathematics for many years. I don't think it's as widely recognized right now as it should be. This is a model of why systems don't scale perfectly. And it helps us to understand how we can make them scale better. Avoid a serial portion of your workload and avoid the coherency or cross-node communication, right? So the new factor that I've added into this equation is on the bottom right. It's kappa times n minus 1. And kappa, again, is a variable portion of the workload. So here's a graph of what this looks like. We've got linear scalability, and we've got Amdahl's law, which asymptotically approaches whatever that 1 over sigma fraction is. And then we've got universal scalability, which has a peak and then drops off. And real systems look like this, right? You've probably all seen benchmarks that drop off after a certain point. So the scalability modeling method is to measure your throughput and concurrency, which are the factors in this equation, perform a regression against the universal scalability law, which allows you to determine the sigma and kappa coefficients. Then you do something, and then you profit. The something is you need some experience and a disciplined approach to the problem to actually turn this into something useful for you. So what we need to model scalability I'll show you a little bit later how we can extend that into performance, is we need throughput and concurrency. And those are two of the things that I said you could derive from the fundamental metrics that you can capture from TCP, which are the arrival times and the completion times. So throughput is easy, right? You just count how many arrivals or completions you have. In a well-behaved system, i.e. one that does not queue to infinity, those will eventually, over a long term, they will be stable. Concurrency is a little bit harder because in the raw TCP output, we don't get to see the concurrency actually against the system. But what we can do is we can sort the arrivals and departures in order, and we can say every time a request arrives at the system, it increments the concurrency, and every time it departs, it decrements the concurrency, and we can calculate a moving weighted average. So in pictures, something arrives at time t equals 0, and query 1 is running until it completes at t equals 3. Something else arrives at t equals 2, and for a brief period of time, the concurrency there is 2. And then it drops back to 1, and then it completes at t equals 7. So basically what I do with the TCP model tool from Percona Toolkit is I sort the TCP arrivals and completions in arrival order, and then I run through them and calculate this information as we go. So the observation time here is 7 units, 7 seconds, or whatever it is. The total query time, the total execution time consumed in there was 8 seconds worth of summed up execution time, and then the average concurrency is simply the 2 divided. So here's a command line. I won't bore you with this, but basically just calculate it and slice it into little intervals, and over those intervals we get throughput and concurrency. And then you can use R, or even GNU-plot actually can do regressions to fit the model to the data and derive those coefficients, the coefficient of serialization and coherency. And what we get is this. This is, again, using exactly the same sample set of data over the same interval. I'm using exactly one file for this whole set of slides. And what I've done is I've fit the universal scalability law to these points and derived the sigma and kappa coefficients, which you can see down here. I've also derived the R-squared metric, which shows you how closely the model fits the data. And then I've plotted the points. This is a scatter plot with concurrency on the vertical axis and, concurrency on the horizontal axis and throughput on the vertical axis. And you can see that At higher levels of concurrency, up around 6 or 8, it starts to look like things break down a little bit and it doesn't fit the model so well. That's because this is a poorly behaved system. I've seen many examples where the system is actually well behaved and fits the universal scalability model quite closely. I would add a caveat that the model is only a model and all models are wrong, but some models are useful, right? So from this prediction, we can see that the universal scalability model says this system is going to peak out at around 3,500 queries per second at a concurrency of 13. Actually, I've got the exact numbers written on the top of the graph there. The concurrency it predicts that we're going to peak at is 3,664 queries per second at concurrency of 13. Now, I can look at this and I can say the system's behaving badly before that, and we're not going to actually reach that with any amount of quality of service. So I can say that we really ought to keep the concurrency on this particular weak cloud server much lower than that. This is basically just proof of what we already knew, that the system was overloaded and we weren't going to be able to get any more out of it on the Amazon cloud. But this is a way that you can forecast out, and I'll come back to this a little bit later about what you can really take away from this data. But this is the model fit to the data points. So the next thing I want to predict is how does performance vary as the concurrency on the system increases. And again, I have a formal definition of performance, which is response time. Performance is not throughput, it's not resource utilization or any of those kinds of things. And if you're from the Oracle world, which I bet a lot of you are, Oracle kind of went the way of performance equals response time science a long time ago with Kerry Millsap and his group. And I follow in Kerry Millsap's and Neil Gunther's footsteps. My footsteps are very small, but I'm trying. So performance is response time, and here's Little's law that says the relationship between concurrency, throughput, and response time. So taking the metrics that we derived on this last graph here, we can actually predict as well the performance of the system. And here I've done it. And I'm modeling, for example, that at around what we say the peak capacity is, 13, it looks like the average response time is going to be somewhere around 0.0035 seconds or something like that. I didn't plot that point on the graph. But you can actually see how the response times are increasing as the concurrency increases. And this should be a very familiar graph to you. If we zoomed out of this, it would look like your stereotypical hockey stick graph that you've probably seen a lot of times, where something has an elbow and suddenly it goes up much faster. If you actually look at the legend on the bottom right, there's a line for the model, that's the red line, and then there's repairman queuing and the measurements in green dots and blue dots. Well, they're exactly the same thing. The measurements and the predictions are exactly the same thing, which is why on the graph you only see the blue dots. The blue dots are obscuring the green dots. So we can actually forecast our performance out beyond what we can measure. So I want to talk a little bit about making sure that you don't have garbage in, garbage out, because if you put garbage into this thing, you will get garbage out. You can't just throw data at the model. You have to actually look at it and see that you're looking at the system in, first of all, that you're measuring the system correctly, and secondly, that you're looking at the system when it isn't misbehaving, such as having a checkpoint or something like that. We saw lots of types of misbehavior on this system, and as a result, the points on the plot were rather scattered, especially at the higher concurrencies. But on a well-behaved system that is running with good quality of service, you will see periods where there's good, clean data that you can use for modeling, and then if a checkpoint or a backup or patrol read on your RAID controller or something else happens, you'll see garbage. You need to throw away the garbage. That's actually one of the reasons why you need to do a time series plot before you get into all of this kind of stuff. Because if there's a massive spike of earthquakey grappiness in your plot, then you need to examine whether that's actually good quality data to feed into your models. One of the first thing that happens on a lot of heavily loaded systems is TCP dump starts dropping packets. There are ways that you can work around that, but you need to be careful because if you are missing some observations, then the techniques that we've just shown here may correlate the wrong responses with the wrong inputs and create phantom long-running queries that never happened, for example. And that'll totally skew your data, and you'll get just garbage out of it. You also want to be aware of extremely mixed or extremely changing workloads. You want to try and measure what the system's workload is rather than something that is too variable to fit into a simple model such as this. So the model will tell you. I mean, if you plot points and it's just an ink blot on the screen, you've either got the wrong data or you need to be looking at it differently or clean something up. You need to do that responsibly. If you remove outliers, keep track of what you removed, because as I mentioned earlier, you need to explain what's going on in the system. And if you throw away the data and you don't remember what you did and why you did it, it's hard to do that later. So it's very important to understand what's actually happening. So when is this modeling actually useful? The universal scalability model gives you two things that you can benchmark yourself and your system against. There's a best case optimistic bound, and there's a worst case pessimistic bound. So when you're looking for bottlenecks in the system, you use worst case modeling. The universal scalability law measures models what's called synchronous repairman queuing, which is worst case. Real systems should, if they are perfect, behave better than this, right? So for example, that second factor in the reason for loss of scalability is caused by intranode communication, assuming that that grows quadratically with the number of nodes. Lots of systems actually only talk to one neighbor, right? So unless your system really is talking to everybody else in the system, the quadratically growing cost of coherency there ought to be pretty pessimistic. You ought to see better than that. So if you model your system against this, and as you do in most real systems, it drops off a cliff and nosedives before the model says it should, you know that something is happening in there and that there's an opportunity to optimize, right? So I've never seen a system that doesn't have an opportunity to optimize, because systems are complex and difficult. And so there's always an opportunity, and basically what this is doing is telling us where that is. At what point in the system's behavior does that become evident, and where could we start to look at it? So for example, if the system behaves very nicely from 1 thread to 2 threads to 16 to 32 threads, and then at 64 threads it really starts tanking and behaving badly, then we should probably measure the system at 64 threads and see what it's doing badly there. 32 threads, 16 threads, it's being good, right? And who knows where the bottlenecks are in the system? It may be in the hardware, maybe in the software, maybe in the network. I've modeled systems where things matched the nice universal scalability law up to a certain point, and then they flatlined. Why did they flatline? Real systems don't flatline. Well, actually, this system flatlined because it was network throughput. So, you know, it could be anywhere. Right? Another thing to look at and be careful about is the shape of the curve. See how this curve is actually concave before it, or convex before it, whatever, concave, convex. You know what I mean? It's, the universal scalability law has this nice rounded shape. It doesn't have a dip and then a roundedness. What's happening here is if you look at the axes of this, you see that it's actually a logarithmic base 2. We're going 1, 2, 4, 8. We're not going 1, 2, 3, 4. And when you shrink things up like that, as many, many benchmark results do in powers of 2 or powers of 10 or something like that, you will see a funny different shape on the graph. So you have to be aware of, don't just sort of mentally look at the graph and say, that's not the shape I'm looking for. You have to be aware of the dimensions on the graph. Yes?
Question on the previous slide. What is PS?
This is, okay, so this is actually a real benchmark that I quickly snagged from something that my colleague Vadim did on our database product, which is called Percona Server. That's where PS is. Yeah. The pessimistic bound, so optimistic bound says the system should scale at least as well as this because the universal scalability law is a worst case scaling, right? The other way that you want to use this is as a pessimistic bound and say, I don't expect to get any better than this. Right, so let's say that we have 3 points here, and we assume linear scalability, and we go up to our whiteboard and we just draw with our marker on a straight edge, and we say, I think, you know, just based on this, it looks like we ought to be able to handle 3 times the load with no trouble, and the real curve looks like this, right? So you want to use this for capacity planning to get some realistic idea of what your capacity might be. What you should not count on getting from your systems is any more than what the system, what the model predicts, okay? Because most systems don't scale as well as they do, as well as they're supposed to. So you don't want to have a nasty surprise when your application gets more popular and your capacity planning estimates turn out to be very, very wrong. So in summary, starting only with these really two metrics of time, the instant in time when something arrives at the server and when it completes, we can measure the query performance easily, and we can find problems that you can't see with your eyes, and we can slice and dice it in lots of different ways to make those things pop out. And we can actually forecast beyond what we can observe with lots and lots of caveats, making sure that you're putting good quality data into the system and being pessimistic when you should be pessimistic and optimistic when you ought to be optimistic. And you can do this for almost any system. All of the data sets that I showed you here were, again, taken from MySQL, but this is, trust me, it's system agnostic. You can do this with Apache, too. And you can do this at a very high level and see how your whole application scales. Not just your database server, not just your web server, but how your entire application is scalable. And you can do this with no instrumentation into the system. You can even do it without access to the systems that you're trying to measure. You can measure the database server from the application server's point of view, for example. You can capture TCP dump from the client side. So this makes it extremely valuable to use TCP traffic as a tool in your toolkit. Finally, play with it. Your mileage may vary. When you go home, you probably won't just pop up pretty graphs and take them to your boss and say, I think we need to acquire more servers or whatever it is. It's going to require, you'll get some noise, you'll throw some stuff away, you'll measure it in a different way. It'll take a little bit of experience to learn how to measure things in a clean way and how to apply a useful model, because a lot of models aren't actually useful for specific cases. Here's the URL to Percona Toolkit, which has the PT TCP model tool in it. One thing I want to mention about that, I talked about being careful about not dropping TCP packets before. This is a Perl tool that consumes the output of TCP dump. What I really need to do is write a C tool that uses libpcap and correlates the TCP sequence numbers, and then we won't have to worry about dropped packets. We'll just throw away observations that we couldn't catch from the kernel. So you just be aware of the limitations of consuming the output of TCP dump. Jake Nash?
Have you thought about using any alternative like system tab or anything to kind of get the same type of information?
So the question is, have I thought about using alternatives like system tap? I showed this to Brendan Gregg from Joyent, who is probably one of the world's greatest dtrace wizards, if not the world's greatest. At the end of the talk, he came up to me and he said, I can't imitate his accent, so I won't try, but he basically said, look, I just did this while you were talking with dtrace. So, yeah. Yeah. System tap, I've had very mixed results, and my colleagues have had very mixed results with system tap. But system tap is nice in that it can measure systems that are not instrumented for you. I love systems that are well instrumented, but most systems are not. That's the reality that we have to deal with. We have to be able to measure things that don't really have a lot of development effort put into making them measurable. And by the way, Postgres has very many areas where it's not extremely measurable. So this is extremely handy. Let's see, back Heroku shirt first.
Yeah, it would be great to see a list of those instruments that you miss, so that people who are writing these patches can, I mean, those are largely not very difficult patches. I think many people will be very happy to see those things. So
Yeah.
Since you seem to have a tremendous amount of experience in that area.
Yeah, so the comment is it would be great to get a list of the instrumentation that's missing. I think, and I have suggested things to various people one-on-one, but I've never submitted anything, for example, to the hackers mailing list or something like that. Unfortunately, I just can't deal with the volume of email on that list. I'm sorry. But I think there are good examples of instrumentation in lots of systems. I cut my teeth on Microsoft SQL Server, which is beautifully instrumented with one problem. The instrumentation is not exposed at the SQL layer in the server, so you actually have to go through Microsoft's tools to get the instrumentation. Oracle is incredibly well instrumented. Oracle DB2 and SQL Server are all very well instrumented. And those are good things to strive after. MySQL is getting a lot better. There's something new in the recent releases called Performance Schema, which it's definitely very much a work in progress, but it's long term it looks like Oracle is going to add at least as good instrumentation into MySQL as they have in Oracle. So it's, there's a lot of good examples of what's out there, What's more interesting, I think, is to look at the tools that people build to consume those metrics, because a well-instrumented system throws so much data at you that you can never even think about it all. And you need good tools to profile it, for example, and bubble the important stuff to the top. You had raised your hand.
Yeah, I was just wondering if you had considered using Postgres or SQL to do any of this analysis work instead of doing it all in your own independent tool. I mean, 'cause you could do windowing functions and things like that to do some of that, gather some of that information.
Yeah, so the question is, what about using a database server instead of writing Perl tools, basically, right? Especially a database server that has sophisticated windowing functions and stuff. And MySQL doesn't have that, right? So it can't really be done easily in MySQL. Yeah, the PLR presentation. That would be a great one, yeah. I had considered that, but most of the time I'm frankly copying around text files and with very limited access to systems. So the nature of my work is that I'm often sort of called to parachute into a system, and I don't have much ability to do things like that. So most of what I've written is command line tools. Most of the time it's all on the grody old command line. There's I should have put Neil Gunther's book here. It's called Guerrilla Capacity Planning. I'm sorry I omitted that. That, of course, is the authoritative source. However, it's extremely dense reading. And if you go to this white paper, the title has MySQL in it, but the principles are universal. And there's a link to Neil Gunther's book in there. If you get through the white paper, I think you'll be well-oriented to get through the book. The book took me about 2 years to really kind of grasp. It's a small book. It's not particularly large, but it took me a while to see how I could apply it. And Dr. Gunther also does guerrilla capacity planning classes, which always draw rave reviews. And there's my contact information. Happy to have conversations about all of this stuff. I'm a total instrumentation and scalability and performance geek, and I love talking about this stuff. I've had some of my best conversations, by the way, with experienced Oracle administrators. They're very scientific, in part because Oracle is so damn expensive that you don't take chances on software and hardware that you've paid millions of dollars of licensing fees for. So that's it. Thanks.